In this video, we're going to look at the last major property of determinants. And that says that the determinant of the transpose is the same as the determinant of A. So the determinant of A transpose is the same as the determinant of A. Now, the proof of this has two cases. One case, case 1, let's assume that A is invertible. If A is invertible, then one of the theorems we proved in class says that A can be written as a product of elementary matrices. So let's say E1 times E2 times E3, etc. times EK. And we know that this is possible if A is invertible. And so this determinant of A equals the determinant of this product. Then from the property 9, where to do the determinant of the product, we could just take the determinant of the individual matrices. This is equal to the determinant of E1 times the determinant of E2 times, etc., times the determinant of EK. Okay? Now, if we go to A transpose, okay, A transpose is basically the transpose of this product, E1 times E2, etc. times EK. And we know from properties of transposes that the A transpose, or the transpose of a product, just writes the product in the reverse order, and we transpose every elementary matrix. Times E2 transpose times E1 transpose. Okay? Now, there are three kinds of elementary matrices. One kind of elementary matrix is basically there to interchange two rows. So E is equal to the interchange matrix. So it comes from the identity, and let's say 3 by 3 identity interchanging the first and third row. Okay, it's just an interchange matrix. Okay, and we know that the determinant of the interchange matrix, if I take the transpose of that, so if I take the transpose of this, what do I get? The first row is 0, 0, 1, that becomes the first column. The second row is 0, 1, 0, that becomes the second column. The third row is 1, 0, 0. It's exactly the same matrix. So if E is an interchange matrix, then E transpose is equal to E. So the determinant of E transpose is the same as E. The second type of elementary matrix is if E does multiplies a row by a non-zero scalar. Okay, so that type of, again, if I start from the identity, let's say we multiply the second row by some number t. It's still a diagonal matrix. Okay, so that produces a diagonal matrix, and this is a matrix rather. And what is E transpose then? E transpose is exactly the same matrix because it's diagonal. And so for that reason, the determinant of E transpose is still equal to the determinant of E. Finally, the other type of elementary matrix comes from taking the identity and then adding a multiple of one row to another. And so if I take the identity, and let's say I add a multiple of the first row, let's say 3 times the first row plus the third row, that gives me a 3 here. But what type of matrix is this? This is a triangular matrix. It'll always be a triangular matrix. And the determinant comes from just multiplying the diagonal entries. So for this type of elementary matrix, the determinant is always 1. Now if I take the transpose of this, it's not the same matrix, but look what happens. The first column becomes a row, the second column becomes a row, and the third column becomes a row. Although the matrices are not equal, this is still triangular, and the diagonal entries are still 1, and so the determinant is 1. So even in this case, the determinant of the transpose is equal to the determinant of E. So for any type of elementary matrix, the determinant of the transpose is equal to the determinant of the original matrix. So going back here, if I were to put determinant here and determinant here, okay, and let me copy that down here. So up on top I had determinant of A equals determinant of E1 times determinant of E2 times etc. times determinant of E3, or EK rather. And we had determinant of A transpose equals the determinant of EK transpose, determinant of EK minus 1 transpose, times etc. times determinant of E2 times determinant of E1 transpose. There we go. But because in light of our discussion of elementary matrices having the same determinant as their transposes, I could just remove all the transposes. And that's still okay. And now these are just numbers. I can write them in any order I want. As a matter of fact, it's the same as writing this order. So as a matter of fact, we just proved that the determinant of A transpose is equal to the determinant of A. Okay? And just to summarize here, this is assuming A is invertible. Now, let's go to case 2. In case 2, the other possibility is A is singular. If A is singular, then the determinant of A is equal to 0 from one of the properties we proved above. But another thing we know is that if A is singular, then A transpose is singular. And for the same reason, the determinant of A transpose is equal to 0. So in the case 2 where A is invertible, both A and A transpose have 0 determinant. And for that reason, the determinant of A transpose is equal to A, and they're both equal to 0. So this proves the property, number 10, that A transpose has the same determinant as A. And the consequence of property 10 is huge. Okay? That means everything, so an important consequence is consequence of property 10 tells us that everything that was true about rows, so everything we know about rows and determinants, is also true about columns. For example, we had a property that said if two rows are the same, then the determinant is 0. So having said that, now we could say if two columns are equal, then the determinant is 0. Another example is to say we had a property above that said if we have a row of zeros, then the determinant is 0. So we could say if we have a column of zeros, then the determinant is 0. And one more. If one column is a multiple of another, column, then the determinant is 0. Okay? And then the linearity tells us we could actually factor a scalar from a column. So if here I had the determinant of 1, 2, 3, 6, 6, 6, 7, 8, 9, then let's say for some reason I wanted to factor out 6, I could do it from a column. So I could keep the first and third column the same, and I could just factor out a number from a column if I want to, just like I could do it with rows. And by the same token, I could use linearity to break up a matrix. Instead of now keeping a row the same, I could decide to keep a column the same, and then write it as a sum so that I have a plus 0 and then 0 plus c. So this is also doable. Okay, so linearity is preserved in columns as well as rows because of this property. So this property that tells us the determinant of the transpose is the same as the determinant of A has, basically everything we've learned from the previous properties now is true about columns. So that's a very, very nice thing to know.